So let's start the class. I think let me just have a look at the paper of 31st January shift 2, and let me see how many of you how many you would have done. You can see this, right?
Yes, sir.
Yes. Okay. Physics. The first question, I don't think you would be able to do it. We had not
Y-
discussed this. X-rays, UV rays, infrared. I don't
Yes,
think you would believe it. Adiabatic process, we have done 1500 questions on this one, right? You would have done this, correct?
yes, sir.
Two balls are projected with speed. We have done so many questions on this. You would have done this, correct? No problem with this one. H max and ratio you had to find out, right?
Yes, sir.
Ionization energy we have not done, so you would not have been able to do this. This one was a tension at the lowest point, right? T minus mg is equal to mv square by L, right?
Yes, sir.
So this was easy. This definitely you would have done. It was all 11 standard.
Yes, sir.
This is we have done so many questions on SHM. You would have done this, right?
Yes, sir.
Projectile one, we have done so many questions on projectile, different angles, different things. Definitely you would have done, correct?
Yes, sir.
Weight of body on the surface earth, we have done it so many times, correct?
Yes,
You would
sir.
have done this. Magnetic field we have not done, so you would not have been able to do this. Young modulus we have not done, so I will not come into that. Heat is I square R into T. If you knew this formula, you could have done this, but we had not covered electric current. This is AC. You would not have done
I
this.
have done it correct, sir. 16H.
Good, good. Then this 13 you would not have done because it is AC, so you will not be able to do it. Length of refractive index, change in focal length. I had given you that formula, right?
Yes,
For
sir.
lens in air and lens in water, right? So this
Yes,
is
sir.
the answer. Moving coil galvanometer, we are not done this, so I don't expect you to do this. Other questions are not there. This is LCR circuit. This see, remember same question we had done. Thickness of the disc. Same
Yes, sir.
question here. See, same question here. Thickness of the disc. This is V is equal to U plus AT mu. You have to find out the value of mu. You would have done this. Stone is dropped. You would have done this. Yes or no?
Yes, sir.
I had given you the formula of this, right? Height reached and all those.
Uh,
How? What is the total distance travel? I had given you the formula. Yes or no?
yes, sir.
Magnitude of displacement. You would have found out this magnitude. Young double slit experiment we had not done. So I think everything was there. We had covered. The only thing probably you would not have been able to do if we have not covered it, right?
Yes, sir.
Okay, good. If you have done these many questions only with 11 standard, that is great because then once we are done with the course, and I think I would be able to do it. I'm trying to speed up things so that I'm able to complete your course by the end of March. Probably I would be able to wind it up. Anyways, let us move ahead and move on to Gauss law. That is what we are going to discuss today. Gauss law. In yesterday's class, we had seen the magnetic field due to different types of charge distribution, and we had seen um, the electric lines of force. Electric lines of force are imaginary lines drawn in such a way that the tangent at any point gives us the direction of electric field at that point. The lecture is there, is already recorded. If you have missed it, you can see it in the recording. Electric lines of force, we had done some questions on electric lines of force. I think in this session or in the previous one question had come for that. Okay, that is not in your session probably. I think in your session, one question had come where they had asked
Electric field is at
electric
any
field
point
and
at a,
electric field and electric potential, yes, something
yes,
of
sir.
that nature. Whether the electric field will be zero or electric potential would be zero. We had not covered potential, but we had covered electric field. I think they had given some positive charges were there, and whether electric field can be zero and potential can be zero, something of that nature, right?
Yes, sir.
So electric field can be zero, but electric potential will not be zero. You can take it from gravitational potential. That was the
Yes,
correct option. Electric field would be can be zero, but electric potential will not be zero. Did you mark that option?
yes, sir.
Good. Then that is also correct. So I don't have to go back. We had seen questions of on electric lines of force in the sessions is not coming. Maybe in the next session, where in April you might see this question. We have done this question on electric lines of force, a couple of questions, and I think that couple of questions would cover everything that can come in your exam. We'll now move on to something known as the Gauss law. In one of the session, I found a question on Gauss law as well. Gauss law is coming anyways. Coming or not coming, we always need to cover Gauss law with all sincerity. Gauss law. What is this Gauss law? Any idea what is this Gauss law? Hmm? No idea. To understand this Gauss law, you did 18, 19 question in physics. What about chemistry and maths?
Sir, in chemistry, I have did 16 questions and in maths, 9 questions.
Okay, not a problem.
Hmm.
So in total, you have done somewhere around 45 questions, right?
47 or something.
47. If 40 are correct, you have cleared JEE. If 40 are correct, you have cleared JEE. So you will get somewhere around 153, 150, 150 marks. That is good enough to clear JEE. That too only studying 11th standard. Gauss law. What do you mean by Gauss law? To understand Gauss law, we have to first move on to something known as electric flux. To first understand the term which is known as electric flux. What do you mean by electric flux? Any idea? What do you mean by electric flux? In the last class, we had seen that electric field lines. We imagine electric field in terms of electric field lines. Then, how do we define electric flux? What is electric flux? Anyone has heard? Anyone has heard what is the meaning of electric flux? Now, if I have to define electric flux, I can define it in this way. Electric flux through any surface is the measure of the number of electric field lines. It is the number of electric field lines passing normally to the surface. Passing normally to the surface. The total number of electric field line passing normally to the surface. If I have a surface, let us say, let me draw a surface. Let me draw a plane surface like this. Draw a plane surface like this. This is a square surface, let us say. And if I say 10 electric field lines are passing through the surface perpendicular, this cross means going into the plane of the paper. If 10 electric field lines are crossing this surface perpendicularly, I can say that electric flux through this surface would be equal to 10 SI units. That is how we can define flux through a surface. This electric flux through a surface is denoted by the letter phi. And what type of quantity is this? It is a scalar quantity. Electric flux through a surface is a scalar quantity. It is the total number of electric field lines which are passing through a given surface. What is the SI unit? And what is the dimensional formula? And remember these SI units and dimensional formula, because many a time questions are coming on this dimensional formula and SI units. There you should not be thinking about the SI unit and calculating the SI unit and calculating the dimensional formula. You must remember this dimensional formula. This is given by this electric field. Number of electric field lines passing normally to a surface is known as electric field. Electric flux, denoted by the letter phi. It is a scalar quantity. Have you noted this down? Okay, I'll give you 2 minutes. Note it down. Let me know once you are done. That was electric flux. Now, we have already seen electric field intensity or intensity of electric field. And intensity of electric field is denoted by this E vector. Now, this is a vector quantity. Electric flux is a scalar quantity. How are these two related to each other? Electric field intensity gives us how strong or how weak the field is. Electric flux is talking about the number of field lines, so we may understand that they are probably referring to the same thing, but how are they related to each other? So this is the time where you can understand what is electric field intensity. Electric field intensity is again the number of electric field lines passing per unit area, passing per unit area, perpendicular to the area. So electric field intensity, it's a vector quantity. If electric flux is the total number of electric field lines, electric field intensity is the number of field lines or the density of field lines. How many field lines are crossing a particular section or particular point per unit area in a direction which is perpendicular to the area. So that is how you can understand electric field intensity or electric field. Now, what we can see over here is this area coming into the picture. Now, as soon as this area comes into the picture, we must understand that area in physics is sometimes, many times, treated as a vector quantity. Area in physics is treated as a vector quantity. Area vector. Now, if area is a vector, then it must have a magnitude, it must have a direction. What is the magnitude of area vector and what is the direction of area vector? Anyone, any idea? What is the magnitude of area vector and what is the direction of area vector? The magnitude of area vector is same as the area of the body. Every surface will have some area. The magnitude of that area, the value of that area, the magnitude of area vector is nothing but the area of the body. If it is a square, the magnitude of area vector will be a square. A square is the magnitude of area, is the area of that body, the area that we get from maths. That is the magnitude of area vector. The direction of area vector is what we must understand. The direction of area vector is along the outward normal. It's taken normal to the area. So if I have an area like this, the area vector is taken normal to this. If I have an area like this is a body which has an area. If I talk about this point, the area vector of this point is outward like this. The area vector of this point is like this. The area vector at this point would be going like this. Do we understand this? Do we understand this? The
Yes,
direction
sir.
of area vector is taken as the normal. Now, you must understand that there are two types of areas that we are going to deal with. One is known as an open surface. The other one is known as the closed surface. Surface, whenever we use the word surface, surface means an area. Now, what do you mean by an open surface and what do you mean by a closed surface? Any surface that encloses a volume is a closed surface. This bottle is a closed surface. This room, if I close the door and is not open from anywhere, it is a closed surface. This wardrobe that you see is a closed surface. Any body that encloses a surface, that encloses a volume, is a closed surface. This is a closed surface. Do we understand this? It has a volume. You can store something here. So this is a closed surface. The area vector for a closed surface is always outward normal. For a closed surface, the direction of area vector is always the outward normal. And that is what it is mentioned here. Outward normal. So if I have to find out the direction of area vector of any point, I will take the outward normal here. That is defined for a closed surface. Then what is an open surface? If a surface is not closed, it is open. This scale is an open surface. This table I'm writing is an open surface. This card is an open surface. It does not enclose a volume. I can't put anything here. Open surface. This is a closed surface. But if I just open it, now these two become open surfaces. This is an open surface. Because if I put anything, it will just fall down. Now this is an open surface. This is also an open surface. But now this becomes a closed surface. Do we understand this? In a closed surface, if I move here, I will always remain on the outer surface. I will not be able to go inside. If it is an open surface, I will be able to go inside it. That means it is an open surface. Do we understand this?
Yes,
Open
sir.
and closed surface. For a closed surface, area vector is taken as outward normal. For an open surface, well, you can take it outward normal or inward normal, doesn't matter. For an open surface, area vector is always told to you that it is in this direction. For a closed surface, area vector will not be told to you. You will have to always assume that area vector is in the outward normal direction. Do we understand this?
Yes, sir.
Pakka everyone? That is all about area vector, closed surface and open surface that you must understand. I'll give you a minute to note this down. We've understood open surface, we have understood closed surface. Then we can see the relation between electric flux and electric field. So that is the next heading that we are going to write. Relation between flux and field. Now how will you relate a scalar and a vector? Electric field is a scalar. Electric flux is a vector. Yes, my dear friends. How are you going to relate electric flux with electric field? Any idea?
So any dot product?
Yes, you will have to take the dot product into the picture and you can understand how the dot product will come. How the dot product will come.
Sir, flux is equals to electric field dot area vector.
Yes, that would be the only way you can create a relation, and that would be the way to go forward. The relation between electric flux and electric field would be in terms of the dot product. So the relation would look like this. What does it look like? Electric flux, a small amount of electric flux d phi will be written as E dot ds or dA. That means if I have a small area like this, drawn it as a small area, the area vector of this area goes like this, ds vector, and the electric field is going in this direction like this. The flux, electric flux through this small area would be given by this formula. The total flux through this area will be integral of E dot ds. Do we understand this? Yes or no?
Yes, sir.
This is how we can write the electric flux through this given surface. Now, there is a small thing that you must understand, may not be so vital. Whenever I write the integral like this, it is actually integral over a open surface. So, electric flux through a open surface will be integral like this, E dot ds. If I have to write it over a closed surface, I will write it also like this, but I would put a gola here. This gola means that it is a closed surface. Do we understand this?
Yes, sir.
So integral over open surface is written like this. Integral over a closed surface is written like this. Now this is how you write it in maths. How do you say? So electric flux through an open or a closed surface is written like this. Now if I have to speak this in word, I will write it like this. Electric flux through an open surface is the surface integral. It is the surface integral of electric field. Do we understand this? Electric flux
Yes, sir.
is the surface integral of electric field. If it is over a open surface, we will say surface integral of electric field over a open surface. If it is closed surface, we will say surface integral of electric field over a closed surface. Do we understand this? Do we understand this? Yes or no?
Yes, sir.
I'll give you 2 minutes so that you can note this down. Let me know once you are done. Okay then, so we have seen when the flux is going to be positive, when the flux is going to be negative, and when the flux is going to be zero. If the angle is acute, flux is positive. If the angle is obtuse, flux is negative. You can say this in a different way. If we are talking about a closed surface, if the flux is going out of the surface, it will be taken as positive. If the flux is coming into the surface, it will be taken as negative. Is the same thing said in a different way. Do we understand this? Yes or no?
Yes, sir.
Okay, I hope you have understood this. Now you can take some special cases of this flux. Now these are the cases that might normally come. Case number one, when the electric field is normal to the surface. When the electric field is normal to the surface, in that case, flux would be E into S into cos of 0. Cos of 0 is 1. So the flux will simply become E into S. Do we understand this? Yes or no? I'll give you a minute to note this down. The next case might happen when the electric field is parallel to the surface. We call it grazing electric field. When the electric field is parallel to the surface, then the flux, the number of electric field lines which are passing normally to the surface becomes zero. Area vector angle between area vector and electric field becomes 90 degrees. In that case, the flux becomes zero. Do we understand this? Noted. We have seen the SI unit of electric flux. It is also known as Gauss. Did I tell you that or not? I may have missed this. SI unit of electric flux. You can also call it Gauss. So you can just write here, this is also equal to Gauss. You can also call it Gauss. So just remember this. They might just ask you. Okay. Let me give you a question. And the question is here. The electric field in a region is given by E vector is 3 by 5 E naught I plus 4 by 5 E naught J, where E naught is something. Find the flux of this electric field through a rectangular surface. I'll give you a minute to give this. The surface.
Sir, it is 240.
The surface is parallel to the YZ plane. If the surface is parallel to the YZ plane, the area vector, where will the area vector of the plane go?
Along x-axis,
It will
parallel
go
to
either
x-axis.
along plus x or it will go along minus x. It is not specified, so we will take it along plus x. So you can write your area vector S vector as 0.2 I, and then you simply take the dot product of electric field with the area vector, putting the values, and you will get the answer. And the answer is very correct, 240 Newton meter square per coulomb, or you can call it 240 Gauss. Do we understand this? Do we understand this?
Yes, sir.
A point charge is placed at the corner of the square of side length A. The diagram is not a part of the question, but I will just show you the diagram so that you can give me the answer quickly. A point charge Q is placed at the corner of a square of side length A. What is the flux through the square? I'll give you 2 minutes to give me the answer. If you talk about this point charge, it will emit electric field in all the directions. But if you talk about this particular surface, the electric field lines which will be emitted by this, or the electric field will be going like this throughout this surface, yes or no?
Yes, sir.
And the area vector would be perpendicular to the electric field
Electric
lines.
field.
Therefore, the number of electric field lines which are cutting this surface, passing through this surface, is zero, and therefore the answer for this one is 0. Do we understand this?
Yes, sir.
Everyone understands this?
Yes, sir.
Then we can quickly go through a concept very quickly, the concept of solid angles. the concept of a solid angle. To understand the concept of a solid angle, we must understand the concept of a plane angle. What is a plane angle? The plane angle is the angle that
Between the normal.
all of us know. All of us know this is a plane angle. What is a plane angle? Plane angle is the angle subtended by an arc of length dl. This is the small angle which this arc subtends. Yes or no? The small angle d theta, which is nothing but dl divided by r, is known as the plane angle subtended by this. Yes or no? No or yes?
Yes, sir.
This is the plane angle subtended by this. Now, the same concept can be extended if instead of a arc of a circle, if instead of a arc of a circle, if instead of a arc of a circle, we have a line segment. We have a line segment also, we can extend the same concept. The angle subtended by this line segment will be equal to dl by r. 1 minute, you may not write this, I'll just cut it off. Now the same concept can be changed to a line segment, and this is a better diagram to understand it. A line can also sustain an angle at any point. You can see this dl is the line segment. That line dl is the line segment. Do we understand this? D theta is the angle that this line segment or line is subtending at any point. The distance of this point from the center, from the point, the distance of this line from the point is r. Then there is a vector r vector that we have drawn, and there is a vector n vector which is perpendicular to this line segment. So how do I define the angle subtended by this plane segment? I find out the angle between r unit vector and n unit vector, and the plane angle subtended by this line is given by this formula. Do we understand this?
Yes, sir.
Just remember this. No one is going to ask you this. You just have to remember this. It will be dl cos theta. dl cos theta. dl cos theta will be that component of dl which is perpendicular to it. Okay. dl cos theta divided by r. Do we understand this?
Yes.
This is the normal angle theta radian subtended by a line at a point. I'll give you 1 minute to note this down. Then the same concept can be extended to solid angle. Solid angle is the angle subtended by an area. Now, to understand the angle subtended by an arc, we took an arc of a circle. To understand the angle subtended by an area, we take sphere, and we take a small area of that sphere. Whatever angle, solid angle, it subtends at the center of the sphere is given by dA by r square. This is just like your cone of your cone of ice cream. If you think about the cone of your ice cream, if you think about the cone of the ice cream, it subtends an angle at the apex. Do we understand this? Yes or no?
Yes, sir.
That angle is like this. Do we understand this? What I'm saying? This, that angle is like this. If I just want to show it, probably I would be able to put this in one more diagram here. Here, if you can see the cone. I join each part of that circle of the cone to the apex of the cone, and I will see a solid angle like this. Do we see this solid angle here? Do we
Yes,
see
sir.
this solid angle here? That is known as the solid angle. Solid angle is the angle subtended by an area at any point. If it is a sphere, the angle subtended by a small area of the sphere at the center is dA by r square. If it is any other area, I will take the angle between the area vector n vector and this r vector, that is your angle theta. Do we understand this?
Yes.
So the small solid angle subtended by this one will be dA cos theta divided by r square. Will you remember this?
Yes, sir.
Give you a minute to note this down. Then you can note down some important points about this. About solid angle. A closed surface, any surface which is closed, this is a closed surface. At any point which is inside this surface, internal point, the total solid angle that the surface will subtend at any internal point is 4 pi. SR means steradian. SR means steradian. Any closed surface will subtend 4 pi steradian at any internal point. Do we understand this, what I am saying here?
Yes, sir.
That means if I have any closed surface like this, just one example, at any internal point, it will subtend at an angle equal to 4 pi steradian. This is same as saying any closed loop at any internal point I have a closed loop of any size, any shape at any internal point O. How much plane angle will it subtend?
4 pi steradian.
Take a long breath.
2 pi, sir. Sorry.
Steradian?
Radian, sir.
Steradian is for solid angles. Radian is for plane angles. Take a deep breath and then give me answer. Any closed loop at any internal point will subtend an angle of 2 pi radians. Do we understand this?
Yes, sir.
A triangle at any internal point, the total angle is 2 pi. Square, pentagon, hexagon, heptagon, whatever gun, circle, loop, at any internal point, the total angle, plane angle that it will subtend would be 2 pi. Do we understand this, or this has gone above our head? Saying bye bye.
Understood, sir.
That was internal point. What about external point? What will be the solid angle subtended by any closed surface at any external point? And the answer would be 0. Do we understand this?
Yes, sir.
This is similar to saying what? Any closed loop substance a plane angle of 0 at any external point. Do we understand this?
Yes, sir.
Everyone understands this? Yes or no?
Yes, sir.
I'll give you a minute to note this down. Let us move ahead and solve this question. And in one question, we are going to solve a lot of questions. Let us say we have a cube and let us name it A, B, C, D. This is A, B, C, D. So this will be E, F, it will be G and H. How many surfaces, how many faces a cube has?
6.
6 faces. You can see those 6 faces, yes or no?
Yes, sir.
Let us also say that your x-axis, your y-axis is like this, and your x-axis is like this. Just for the sake of argument, your x-axis goes like this. Your origin is at point C, let us say. Okay. Now, how many faces we have? Let us name them. A, B, C, D. That is the first face. E, F, G, H. That is the second one. Then A, E, G, C. This taraf, this face. You understand, na? The
Yes,
cube
sir.
is kept like this. So this face, which is facing me, is A, B, C, D. The face which is facing you is E, F, G, H. This is the face A, E, G, C. Do we understand this?
Yes, sir.
Then this is the face B, F, D, B, F, H, D. Yes or no?
Yes, sir.
B, F, H, D. Then we have the upper face A, B, F, E, and then we have the lower face C, D, H, G. These are the 6 faces of the cube. Do we understand this?
Yes, sir.
Make a line so that they are segregated from each other. Okay, and in the last slide, I have total flux to the entire cube. Okay, now let me give you different values of electric field, and let us try to find out what is the answer. The edge length of the cube is A. The edge length of the cube is given as A. Now in first case, your electric field is, let us say, E naught I hat. The electric field, let us say, is E naught I hat. In first case, the value of electric field is E naught I hat. Now, E naught I hat is the electric field. Can you tell me the flux through all the 6 surfaces? I'll give you a minute to do this. So what is the flux through the surface A, B, C, D?
0, sir.
Electric field is along x-axis and the area vector of this will come along k-axis. Yes or no?
Yes, sir.
So the answer for this will be 0. The answer for this will also be 0. Yes or no?
Yes, sir.
What is the flux through AEGC? AEGC is this surface. The area vector will lie like this and electric field will go like this. So the
E
answer
naught.
will minus E naught A square. Yes or no? Area vector is like this. Electric field is like this. The flux through this part will be same but positive. Yes or no?
Yes, sir.
The flux through the upper and the lower surface again would be 0 because area vector is perpendicular. Yes or no?
Yes, sir.
The total flux would be 0. Do we understand how I have done this?
Yes, sir.
Everyone understand this? Okay, let me just change it to E naught J hat. If I make it as E naught J hat, then what is the answer? I'll give you 1 minute to do it. So what are the answers for this one?
Sir, total is 0, sir.
Total is 0. What about the other surfaces? What about the four surfaces?
Sir, first four surfaces are 0,
First four surfaces are 0.
and fifth surface is minus E naught A square, and sixth surface is plus E naught A square.
0, 0, 0, 0. Total is also 0. The fifth surface, it will be plus, yes or no?
Yes, sir.
And this one will be minus. Do we understand this? Let me now put it this way. E1 I hat plus E2 J hat plus E3 K hat. Now can you give me the answer? I'll give you a minute to do this. So what are the answers for this one? A, B, C, D. What is the
Sir,
flux for the surface A, B, C, D?
E3 A square, sir.
E3A square. What about the flux through EFGH?
Minus E3 A square.
Minus E3A square. Do we understand this?
Yes, sir.
Then AEGC.
Minus E1 A square, sir.
Minus E1A square. This will be plus
Plus E1 A square.
E1A square. ABFE.
Plus E2 A square.
Plus E2A square. This will be minus E2A square. The total answer is 0. From here, we can also understand one more thing. The total flux is 0, given that this is like this. That means if a closed surface, important point, if a closed surface of any size or shape is placed in a uniform electric field in any direction or in any orientation, in any orientation, closed surface, this placed in a uniform electric field, no matter how I place it, the total flux would be
0.
the total flux would be 0. It's a very important case that we must understand. I'll give you a minute to note this down. Now see, if you have any body of any open body of any irregular shape, it has one surface square, one side square, you can take a cone. If the cone is closed, the total flux passing through the cone would be 0. Yes or no?
Yes.
That means whatever flux is passing through the entire curved surface, the ulta flux is passing through that circular part. Yes or no?
Yes.
That means if any question comes where we have an irregular shaped body, but on one side you have a circular or a rectangular or a square shaped body, once you close that body, the total flux passing through that irregular shape will be equal to the flux passing through the square or the triangle or the circular part. Do we understand this?
Yes.
So any shape body, whether it may be given like body number 1 or it may be given as body number 2, hemispherical shell, or it is a simple circular body, the flux passing through all these bodies will be equal. Yes or no? Do we understand this?
Yes, sir.
I'll give you a minute to note this down. Can we come to this question where we are supposed to find out the flux passing through the ring? You have a point charge q and you have a ring of radius r, and this point charge q is placed at a distance of x from the ring of radius r. You are supposed to find out the flux, because this point charge will create electric field, and because of this electric field, number of electric field lines will pass through the ring. This the point charge is placed on the axis of the ring. Do we understand this question? Yes or no?
Yes, sir.
Now, I will not ask you to solve this. I will just try to make you understand what is the similarity between this question and a different question. Whether it is this question or this question could be okay. Now, uh, if I have to find out, let me take an example. If I had to find out this is a ring, or I can think it of, if it is made up of an area, I can think it of as a disk. This disk has a area pi r square. Yes or no?
Yes, sir.
Now this disk, and this is a point on the axis of the disk. If I call this angle as phi, it is just like the apex, the semi-apex angle of a circular part of the cone on the axis of the cone. Yes or no? It looks like a cone, right? It is a cone, right?
Yes, sir.
Yes or no? Now this cone, the circular part of this cone, the circular part of this cone will extend, will. This is the will subtend a solid angle at the apex of the cone. Yes or no? Do you remember that solid angle? That solid angle, this solid angle omega.
Yes, sir.
It will subtend a solid angle at the apex of the cone. Yes or no? If I call this solid angle as omega, this solid angle is given by this legendary formula 2 pi into 1 minus cos of phi, and this is the best way that I remember it, where phi is the semi-vertex angle. If you don't want to write it in terms of semi-vertex angle, you can write it in the form of 1 minus x by under root of x square plus a square, x square plus r square. Do we understand this? This is the solid
Yes, sir.
angle subtended. Listen to me very carefully. This is a very important question, because you can get a variation of this question not in JEE Main, probably in JEE Advanced. Now, this is the solid angle subtended by this disk at this point. Now, if someone would have asked me that this disk has a surface charge density sigma, then this disk will create an electric field at this point where this point charge is placed. Yes or no?
Yes, sir.
What was the electric field? I am only talking about the magnitude of that electric field that this substance at this point where this charge is placed. Let me call this point as point P. What is the magnitude of electric field if this disk had a surface charge density sigma? What was the electric field created by the disk at that point?
Sigma by 2 epsilon naught into 1 minus cos theta, that is 1 minus x by under root x square plus r square.
Do you understand why they are looking same? Because they come from the same concept. Here we have sigma by 2 epsilon naught. Here we had 2 pi. Because the way this solid angle is created or calculated and the way this electric field is calculated, they are exactly same. The only thing is solid angle only talks about the area. Electric field, apart from the area, because this area has a charge, therefore this sigma and epsilon naught also come. Do we understand what I'm saying here?
Yes, sir.
Now I reverse the question, and now I come to the question, what is the flux of this electric charge passing through the ring? And the answer for that flux is Q by 2 epsilon naught into 1 minus cos phi. And again, you can see the similarity, because the way this flux of this point charge is calculated about this is same as calculating the solid angle is also same as calculating the electric field created by this. If you remember one, you should be able to remember all. Do you understand this? Or just gone
Yes.
above and saying bye bye? Huh? We understand this?
Yes, sir.
Pakka? I'll give you a minute to note this down. Let's move ahead. And in moving ahead, we now move on to the heading of today's class, that is the Gauss theorem or the Gauss law. Gauss theorem or Gauss law. And what does this Gauss law say? It is a simple statement which is valid only for a closed surface, and it states that the flux of the net electric field created by all the charges through an imaginary surface, closed surface, Gaussian surface of any arbitrary shape or size, flux through any closed surface called the Gaussian surface, which is nothing but integral of E dot ds. This E dot ds will be equal to the charge enclosed by the surface divided by epsilon naught. This is the statement of Gauss theorem. Have you heard this statement? Yes or no? Yes or no?
Yes, sir.
This is the statement for Gauss theorem. The flux through any closed surface would be equal to the charge enclosed by the surface divided by epsilon naught. Now, if I have, let us say this is my surface. Remember, this is a closed surface. This closed surface is known as the Gaussian surface. This closed surface is known as the Gaussian surface. I have some charges inside the surface, plus Q1 minus Q2 minus Q3 plus Q4 plus Q5 minus Q6 and so on. So what does the Gauss theorem state? It states that the flux through of this, the net electric field created by all these charges through this closed Gaussian surface will be equal to the charge enclosed by the surface. How much is the charge enclosed? Q1 minus Q2 minus Q3 plus Q4 divided by epsilon naught. Remember, this electric field is the net electric field created by all the charges. So it will be equal to E1 plus E2 up till E6 and so on. This is what the Gauss law says. If you have a closed surface placed anywhere in the universe, and if you want to find out the flux of electric field created by all the charges in the universe through this surface, what you got to do, you only need to open, see how many charges are inside and divide it by epsilon naught. Do we understand this? Do we understand this? Yes or no? We understand this? Give you 2 minutes to
Yes,
note
sir.
this down. Then we write some important points. The first important point, it is only valid for any closed surface. Remember, the surface must be closed no matter what is the size and the shape of the surface. Do we understand this? First, listen to me, then I'll give you time to write. The second point is the charge Q includes the algebraic sum of all the charges inside the surface. Do we understand this? If charge is positive, you take it positive. If the charge is negative, you will take it as negative. Do we understand this?
Yes, sir.
The electric field which you are taking is the net electric field produced by all the charges, but the charges that you are taking are only the charges which are present inside the surface, which are coming inside the surface. Do we understand this?
Yes, sir.
Okay. Now, if it is a point charge, the Gaussian surface should not pass through the point charge because that will not make any sense. Gaussian surface should not pass through a point charge, but it can pass through a continuous charge distribution. So you cannot create a Gaussian surface which passes through a point charge, whether the point charge will come inside it or it will come outside it. Do we understand this?
Yes, sir.
Okay, just wait. I will have more points if I can put more points. Flux through this Gaussian surface is independent of the position of charge. Do we understand this?
Yes, sir.
Is independent of the position of the charge. Does not depend. It does not depend on the position of the charge. Outward flux would be taken as positive and inward flux would be taken as negative. Do we understand that?
Yes, sir.
If the flux through any closed surface is zero, if the flux through any closed surface is zero, it does not imply that the electric field is zero. It only implies that the charge enclosed is zero. Do we understand this?
Yes, sir.
But if electric field is zero, then obviously the flux is zero. Do we understand this? Yes or no? No, yes.
Yes, sir.
I'll give you 2 minutes to note this down. Then let's move ahead and solve some question. This is the first question that I'm going to give you. You have to find out the flux through this given Gaussian surface, and I'll give you 2 minutes to do this. And the answer is 3 microcoulomb divided by epsilon naught. You just have to look at how many charges are coming inside. 2 plus 4, 6 minus 3 microcoulomb. So the flux will be going outward. Do we understand this? Yes or no?
Yes, sir.
What about this one? What is the flux through this system, through this closed surface that I have created? What is the flux through this closed surface that I have created?
Zero, sir.
Zero, because the net charge in it would be zero. Do we understand this?
Yes, sir.
So what we can do is we can now write some important things that will come as questions. So these are basically questions, but we are writing them as note. Note number 1, if you have a closed surface which is placed in a field and it may be a uniform field, It may be a non-uniform field. If there is no charge enclosed, the flux link through that field would be zero by Gauss law. Do we understand this? Yes or no?
Yes, sir.
So here you can see two surfaces placed. The first one placed in a non-uniform field, the second one placed in a uniform field, but you can see there is no charge enclosed by the two surfaces, and therefore the flux of electric field, in first case it was uniform electric field, in the second case it was non-uniform electric field, the flux is coming out as zero. Do we understand this? Yes or no? No, yes.
Yes, sir.
Everyone understands this?
Yes, sir.
Now if you have only one charge and a body enclosing the entire charge, the flux through that entire body, remember that has to be a closed body. Do we understand this?
Yes, sir.
That has to be a closed body. The flux through that closed body would be equal to Q by epsilon naught. Q by epsilon naught, no matter what is the shape of the body. And these are the sum of the bodies that you will find in the question paper that you will get. I'll give you 2 minutes to note this down. Remember, these are questions that are going to come. Then these are some other cases of zero flux. When will be the flux through a closed surface? Remember, we are talking about closed surface will be zero. If the net charge is zero, you understand what is this that is shown here? Dipole. Have you seen this dipole?
Yes, sir.
The net charge of the dipole is zero. So if a dipole is enclosed in a Gaussian surface, the flux will be zero. If the net charge is zero, flux is zero. If it is placed in a uniform or a non-uniform field and not enclosing any charge, then the flux will be zero. Do we understand this? This point number 3 is a repetition of what we have already written. You may not write it. You just need to write the first 2 points. I'll give you 2 minutes. Then you can see these different cases where closed bodies are placed, where open bodies are placed in a uniform electric field. You can see how you can find out the flux. You can see from this side flux is entering, and from the other side its flux is coming out, so the total flux is going to be zero. So if anyone asks you what is the flux through the curved surface, what is the flux through the open surface, you will be able to calculate it. Yes or no?
Yes, sir.
This is a hemispherical cup. It's open from one side, so whatever flux is entering from one side, the same flux is coming out from the other side. So you can find out what is the flux through the curved surface. It will be same as the flux coming through the circular part. Yes or no? We have already given you that. Yes or no?
Yes, sir.
This cube, whatever flux is entering, the same flux is coming out. Total flux is zero. Do we understand this?
Yes, sir.
In case of a hemispherical cup placed like this, whatever flux is entering in, the same flux is going out. The net flux is zero. Do we understand this?
Yes, sir.
Everyone understands this? Just note it down at important points. That takes us to the next part. Remember, whenever we are talking about Gauss law, symmetry plays a very important role in Gauss law. You can see if they give you a question where you have a point charge which is placed on the circular portion of a hemisphere, and they ask you what is the flux through the hemisphere, how are you going to find out the flux through the hemisphere? You enclose this with one more half part. You understand what I have done here?
Yes, sir.
You enclose the charge with one more half part. Now the total flux is Q by epsilon naught through the entire sphere. So what is the flux through half of the sphere? Because they are symmetrical, it will be Q by 2 epsilon naught. You can calculate it in this form, or you can calculate it from your electric field. No matter what you do, you will get the same answer. Do we understand this?
Yes, sir.
Similarly, if they ask you what is the flux through this one, this half cylinder, so you put one more half cylinder on top of it, the flux through the total full cylinder, it becomes a closed surface, becomes Q by epsilon naught. So flux through any half part becomes Q by 2 epsilon naught. Do we understand this? Yes
Yes,
or
sir.
no? I'll give you 2 minutes to note this down. Symmetry plays a very important role in Gauss law. We have seen that now. The cube wala symmetry. If you have this type of is known as face center cube. Do we understand chemistry? Face center cuboid, face center cube, FCC.
Yes, sir.
Charge is placed at the center of the face, and then they ask you what is the flux through the entire cube. So what do? You enclose it one more cube on one side. The flux through the entire bigger cube will be q by epsilon naught. So flux through any of the part will be q by 2 epsilon naught. We understand this?
Yes.
Then we have this one, the edge center. We place the cube on the edge of any of the C. You will place it here on the edge. So how do I enclose it completely? I will put one cube here, I will put one cube on top here and one cube on top here. So at the center of these four cubes, it will come exactly at the center. Yes or no?
Yes.
Flux through the total structure will be q by epsilon naught. So flux through any one part will be q by 4 epsilon naught. Do we understand this?
Yes, sir.
At center. Then we have, if I place the chart here, I will have to put one cube here, 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 and one cube here. 8 cubes I have to put. Yes or no? 7 cubes extra. Yes or no?
Yes, sir.
Flux through any one of the cubes will be q by 8 epsilon naught. Do we understand this? Yes or no? Symmetry plays a very important role. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note this down. Then this is the next question, sir. If a point charge q is placed at the center of a cube, exactly at the center of the cube, what is the flux through any one face of the cube? What is the flux through any one face of the cube? And what is your answer? What is the answer? No answer. This is the cube. The point charge is placed exactly at the center of the cube. Look for symmetry. What is the flux through any one of the faces? And what is the answer?
Q by A into epsilon naught, sir.
Take a deep breath. Understand the question. A point charge is placed at the center of a cube. What is the flux through any of the faces? Any of the faces. Any of the faces. If you talk about this pink face, what is the flux through this pink face? Or what is the flux through the green face? The green face may be this one. What is the flux through this one? How will you calculate it? How will you calculate it? Symmetry plays a very important role in Gauss law. Do not forget it. Symmetry plays a very important role in Gauss law. What is the flux through this pink surface or through this green surface? The total flux through the cube is q by epsilon naught. Flux through any of the faces. All the faces are similar. All the faces are symmetrical. The flux through any of the face will be how much?
Q by 6 epsilon naught.
Q by 6 epsilon naught. That is the answer, my dear friends. Do we understand this? Oh, it has gone above our head.
Yes, sir.
Saying bye bye. Do we understand this? Or this has gone above our head? Saying bye bye. Huh?
Understood, sir.
A charge q is placed at the distance of a by 2 from the center of a horizontal square surface of HA as shown in the figure. What is the flux of electric field through the surface? This is the diagram. Point charge is placed here, Q. Any idea? No idea? Get idea? Yes, idea? Yes, my dear friends. Symmetry plays a very important role in Gauss law.
Sir, it is same as cube no, sir.
It is same as cube, no, sir. Yes, sir. You put 5 more faces. 1, 2, 3, 4, 5. Enclose it. The answer is 6. Q by 6 epsilon naught. Do we understand this, or this is gone above our saying bye bye?
Understood, sir.
Next question. What is the flux through this cube? So what is the flux through this hemisphere? A point charge is placed exactly at the center, here on the circle. What is the flux through this hemisphere? That's my dear friends.
Q by 2 epsilon naught, sir.
Q by 2 epsilon naught. Okay. What is the flux through this one?
Same Q by 2 epsilon naught.
Okay. Same 2 by Q epsilon naught. Okay. Do we understand this, or this is going above and saying bye bye? I'm going
Understood.
bye bye, bye bye, bye bye. Flux in SI units coming out and entering a closed surface is shown in the figure. Find the charge enclosed by the surface. You'll have 2 minutes to give me the answer. So what you have to find out? You just need to find out the flux enclosed by this surface. Flux through this closed surface. Incoming is 15.
Only 15, sir.
And outgoing is 60. So total flux is plus 45. Yes or no? That
Yes.
will be equal to charge enclosed divided by epsilon naught, and that is the answer, my dear friend. Charge enclosed is 45 epsilon naught. Why are you taking so much time to calculate plus minus? That is the next question. In electrics, there is a point charge placed plus Q. A spherical closed surface is drawn by the dotted line. The electric flux through the surface is 0. A conducting sphere is inserted intersecting the previously drawn Gaussian surface. What is the electric field through the surface? So basically, this pink thing that you see is a conductor, conducting sphere. Do we understand this? Do we understand this?
Yes, sir.
This is a conducting sphere. So I have a point charge and a conducting sphere, and I enclose a Gaussian surface. What is the flux through this Gaussian surface? Do you understand the Gaussian surface?
Yes, sir.
4 options given here. Which is the correct one, my dear friends? I want the correct one. I'll give you 2 minutes to give me the answer. Because of this positive charge, what will happen? The negative charge will shift here and positive charge will shift on the back side. Yes or no? The total
Yes,
charge
sir.
of the sphere will remain 0, but it will attract the negative charge on one side and it will attract the positive charge on the other side. Now we have a Gaussian surface, and this Gaussian surface will enclose positive charge, and therefore the answer is B, non-zero but positive. Do we understand this? Or this has gone above our head? Saying bye bye. Bye bye.
Understood, sir. Like small sign mistake.
Small sign mistake, you get -5, my dear friend. Electric charge uniform distributed along a long wire of radius 1 mm. The charge per centimeter length of the wire is q coulomb. Another cylindrical surface of radius 50 centimeter and length 1 meter symmetrically encloses the wire as shown. What is the total flux passing through the cylindrical surface? You have 2 minutes to give me the answer. You just have to find out how much charge is coming in this much of space. Yes or no? And this much of space has a length of 1 meter. And the charge per centimeter is q. So in 1 meter you will have 100 q. So the answer is 100 q by epsilon naught. Yes or no? No or yes?
Yes, sir.
This is the next question, my dear friends. A charge q is uniformly distributed on a ring of radius r. The diagram is not a part of this, but still. The sphere of equal radius r is constructed with its center at the periphery of the ring. Okay, the figure is a part of the question. Find the flux of the electric field to the surface of the sphere. This is more a question of maths rather than a question of physics. You have 2 minutes to show your time. Q by 3 epsilon naught is correct. You just have to find out how much is this portion. So basically, you just have to find out how much is this angle. Yes or no?
Yes, sir. 120 degrees.
This is 120 degrees. So it will enclose 1/3 of the charge. If it encloses 1/3 of the charge, the flux will be Q by 3 epsilon naught. Yes or no? No or yes?
Yes, sir.
Okay. I think I have. Just give me a minute. Okay. Now remember, symmetry plays a very important role in Gauss theorem, and I'll give you some questions on that symmetry part, which we have already done, but I will try to make you understand other things because they might ask you this one. Now this cube we have already seen. Try to understand the symmetry of this one. This is a face center cube. Yes or no? We have seen that the flux through the entire cube is q by 2 epsilon naught. Yes or no?
Yes, sir.
Let me name the cube as A, B, C, D, E, F, G, H. Now looking at the symmetry, you have to tell me which faces will have same flux. This is placed at the center of BFGC, okay? So I'm looking at the figure, looking at the geometry, looking at the diagram. You have to tell me flux through which part would be same, flux through which part would be different. If you can tell me flux through any part, whether it is 0 or something else, the value that you can calculate, you can tell me the value of the flux through that part as well. Flux through one surface is going to be 0 here, or some surface is going to be 0 here. You have to tell me which flux is 0, which flux is same, and which flux is different. I'll give you 2 minutes. You have understood the question, yes or no?
Sir, all the adjacent surfaces to the surface in which charge is present are same flux.
That means
A, B, C, D, E, A, E, B, F, B, F, G, C. Sorry.
BF, DC, no.
No, in that surface it is 0, sir.
Yes, BFGC, this pink surface, the flux is 0.
0.
Okay.
And
Then
all adjacent surfaces to that
green,
FGC
this green and this green, all these
have
four.
same flux.
And the other one, which is this blue one, the flux would be different. Do we understand this?
Yes, sir.
Okay. Now this one. Through which surface flux is 0, through which surface the flux is same through which surface the flux is different. I can name it A, B, C, D, E, F, G, H. Yes. I'll give you 2 minutes to think. The surface with the same edge, the flux is 0. Then the two surfaces like this, the flux is same. One surface here and one surface here, the flux is same. Do we understand this?
Yes, sir.
This one. Which surface is same and which surface is different?
And other three surfaces have same flux.
So if I call this surface as 1, this as 2, and the bottom one as 3, 1, 2, 3 are 0.
Yes, sir.
The front one 4, this one 5,
Top 6.
and top one 6. It will be same. How much is the flux through 4, 5, and 6?
4, 5,
They are all same. Flux through the entire cube is q by 8. So it becomes q by 24 epsilon naught. Do we understand this?
Yes, sir.
We have already found out, na? Q by 8 is the flux through the entire cube.
Yes, sir.
Q by 24
By
is
3
the
is
flux. Do we understand this? Yes or no?
yes, sir.
Okay. These are more likely the questions that are going to come. Now, this Gauss law can be used to calculate the electric field due to some symmetric charge distribution. And we have already seen those electric field. How this electric field is calculated, I'll just show it to you in 5 minutes. I hope you can follow it quickly and note it down. The application of Gauss law. The first application is electric field due to a point charge. So what I have done, you just look at the process. I have put a point charge and I've created a Gaussian surface. Now, what type of Gaussian surface you create for what type of charge? So this is a table that will tell you what type of Gaussian surface you create for what type of charge. So you can note down this table first. What type of Gaussian surface you must create for what type of charge? For a point charge or a spherical charge, you will always create a Gaussian surface which is spherical because electric field will be going radially outward. Do we understand this?
Yes, sir.
And on all the points of that sphere, electric field will be constant in magnitude. For a line charge or a plane charge, you will have to create cylindrical Gaussian surface. Do we understand this?
Yes.
You know this or you want to note it down?
1 minute.
Note it down. Then you can use this Gaussian law to find out electric field due to a point charge. What do? You assume that this point charge is at the center of this sphere. You create a spherical Gaussian surface of radius r. At all the points, the electric field is going radially outward. It is same in magnitude. Yes or no?
Yes,
And the
sir.
angle between E and area vector, electric field will be going like this, and your area vector at this point will also go like this. So the angle remains 0. Yes or no?
Yes, sir.
So your integral of E dot dA simply becomes E into pi r square, 4 pi r square. Yes or no? Total surface area is 4 pi r square. Yes or no?
Yes, sir.
You can use this to calculate the electric field due to a point charge. You already know the answer. This is how Gauss law is applied. You create a Gaussian surface. You find out how much charge is coming inside the surface. You divide it by epsilon naught. You divide it by the area, and you get your electric field. Do we understand this? But this can only be used for very specific purpose. The first thing is electric field due to a point charge. Have you noted it down?
1 minute, sir.
You already know the formula of electric field due to a point charge. You just need to see how it is calculated using what? Using the Gauss law. You just create a Gaussian surface and you do the needful. Yes or no?
Yes, sir.
Noted it down?
Yes, sir.
You just have to note down how the process. The second thing is you take a uniformly charged spherical shell, which may be a conductor or which may be a insulator, or you take a conducting sphere. The charge will come on the outer surface. Do we understand this?
Yes, sir.
For any external point, you create a Gaussian surface outside. For any internal point, you create Gaussian surface inside. For outside surface, the electric field will become same because the charge enclosed will be Q. But for inside points, there will not be any charge. Therefore, there will not be any flux, and therefore there is no charge, no flux, there is no electric field as well. Yes or no? Do we understand this?
Yes, sir.
This is same whether it is a conducting sphere or it is a spherical shell. Do we understand this?
Yes, sir.
I have already given you that formula, that graph. Yes or no?
Yes, sir.
In one of the sessions, they have asked the graph not for electric field but of electric potential. Once you understand the graph of electric field, I will also give you the graph of electric potential and both of them together. Do you understand this, how this is done? You
Yes, sir.
also remember the graph, yes or no?
Yes, sir.
Pakka na?
Yes, sir.
Now, the next electric field that you can calculate using this is the electric field due to a uniformly charged non-conducting sphere. And here, when you enclose a point inside also, you will have charge coming inside it, and therefore you have field. Do you understand this?
Yes, sir.
So you can derive that formula using Gauss law as well. We have already seen the formula. The only difference is when you have the point outside, the total charge enclosed is Q, the formula remains same. When you have point inside, you only have to calculate how much charge comes in this much of sphere. Do we understand this?
Yes, sir.
Formula we have already seen. You don't have to look at the formula. Do we understand this, or this has gone above our head? Saying bye-bye.
Understood, sir.
Understood? Apart from this, you can find out the electric field due to an infinite line charge. Infinite line charge, if you remember, it was lambda by 2 pi epsilon naught r. Yes or no?
Yes, sir.
You can find out that using a cylindrical Gaussian surface. Again, the same principle. You just enclose a Gaussian surface. You find out the area. Electric field and area vector are going to make zero angles here. Do you see this? So the integral of the upper surface, which is the circular part here and circular part here, electric field is perpendicular. Therefore, this becomes zero and this becomes zero. The net electric field, the net electric flux is only due to the curved part, and that is equal to E into 2 pi RL. Do we understand this for this part which is curved? We understand this?
Yes,
Curved
sir.
area is 2 pi RL. Therefore, the answer becomes lambda by 2 pi epsilon naught L, infinite. So whenever you are asked to find out electric field using Gaussian law, you just have to create Gaussian surface and find out the flux through that Gaussian surface. You have to find out the area of that Gaussian surface, see through which surface the area is the angle 0, see through which surface the area is 90 degrees, and you can find out the flux. This is the electric field due to infinite cheat. We have seen the formula sigma by 2 epsilon naught. Yes or no?
Yes, sir.
So we can use Gauss law to calculate all these things. Remember, whenever a question comes, using Gauss law, you just have to create a Gaussian surface and you have to find out how much charge comes in that surface and divide it by the area and see if it is coming as zero or not. Yes or no? Do we understand this?
Yes, sir.
I think this is more than enough for you to understand Gauss law. I've already sent you the sheet for electrostatics. Yes or no?
Yes, sir.
Just concentrate on that sheet, and you would have realized, since you have already appeared for your exam, that even if you don't do any single question of the sheet, whatever you are doing in the class, Questions are going to come from that part only, and I can assure you that that will happen. If you just do whatever questions we are doing, that is good enough for you to clear the JEE. So I'll end up this class here. In the next class, we'll start with potential and potential energy, and I hope to complete them in 2 classes, so that by the end of this week, Saturday, we might be able to wind up electrostatics and move into capacitance. So that is my aim. Let's see how far we get. If there's anything that I can help you with, please let me know. Else, this is a wrap from my end. Take care and God bless you all. Bye bye.
Bye, sir. Have a good day.